Hello everyone, my name is Hyowon, main author of this paper. Today, I talk about my paper, Analytical Study on after-treatment system for stationary engine. I talk about this paper's introductions. First, let's talk about the diesel engines for emergency generators. In emergency generator, operation inspection should be performed once a week for 30 minutes or more under no-load conditions. In these conditions, large amounts of harmful emissions such as NOx and PM are generated. Data from Ministry of Trade, Industry and Energy of Korea, PM emissions from emergency generators are 770 tons per year, reaching 80% of automobile emissions. Also, emergency generators operate in high load conditions, so amount of noxious emissions by emergency generators are significantly increased. So, emergency generators need after-treatment devices such as DOC, DPF, urea SCR, and AOC, which used in road diesel engines, are also applied to stationary diesel engines for emergency generators. Now, let's talk about diesel particulate filter DPF fundamentals. In DPF, there is a cake layer system, a porous stacking structure. In this structure, ceramic blocks alternately block both sides of the passage, and exhaust gas entering open passage pass through a perforated hole in ceramic wall. In DPF, there is a problem that ash has accumulation during PM iterations. These matters accumulate along the channel or inside the filter, and some of them accumulate as the flow rotates on the end flows of each layer. The main contributors of these accumulations are lubricant consumption rate and sulfur ash, phosphorus, or sulfur, and so on. The filter structures need to minimize this ash accumulation. So, some studies show that asymmetrical channels have been studied to replace honeycomb-shaped channel structures. In deviated regenerations, there are some problems that if DPF ignites the soot particles inside the DPF requires the exhaust temperature to be raised up to 500 to 600 degrees Celsius. In this situation, dust accumulated inside the DPF is burned, and the surface of the channel and plug covered with dust is restored, and restoring the reduction performance. In these programs, thermal stress occurs as the carrier is rapidly exposed to high temperatures. These problems result in poor durability of the carrier or damage inside the carrier. So some studies show that non-destructive DPF measurement using CRS rate is on the way to monitor the damage of DPF. Next, some studies show that injecting fuel into multiple parts from DOC in front of the DPF during the regenerations. In this situation, multi-layered regeneration process can be pursued, so DPF can be regenerated more safely without significantly increasing temperature. So now, I talk about the main topic of this study. Analysis for optimal design of a circular type after-treatment system for small and medium emergency generators. We wanted to find ways to optimize PM NOx reduction efficiency without changing the reference specifications of DOC, DPF, and SCR. So, we set up geometry and placement of urea mixers as separation angles, which are expected to affect flow uniformity. In this study, we need CFD and analysis approaches because Identifying such flow uniformity is a very difficult part to find out experimentally, but CFD analysis can reduce the time and cost for research and development by minimizing trial and error in the optimal design process. So, we studied the NOx reduction method of after treatment systems using CFD to analyze SCR flow uniformity. Now, I will explain about my study's analytical methods. First, analysis models can be introduced. This purpose of this study is interpreting turbulence, and analytical domain access filters is to interpret turbulence using the RNG K-epsilon turbulence model. Also, porous catalysts such as DOC, deviated SCR are established and interpreted of porous medium without considering the channel of the internally generated filter. Next, we use the liquid splitting models proposed by Pitch and Irving. Also, we use the spray collusion model proposed by Baik, used to predict the behavior during a liquid wall collision. Figure 1 shows the geometry of PM NOx reduction system. Next, let's talk about the urea SCR system. The chemical reactions used in the study can be classified into 3 categories: pyrolysis, hydrolysis, and SCR reactions. The reaction processes can be described as below. There is a thermolysis reaction, hydrolysis reaction, and SCR reaction process, which has 3 types of speed: standard, fast, and slow. Next, I talk about the uniformity index. Flow uniformity of ammonia throughout the front of catalyst is an important factor that influences NOx conversion efficiency, catalyst lifetime, and also activation time. Uniformity proposed by Mertens is commonly used as an index of flow uniformity, defined as follows these equations. In this equation, N denotes total calculation cell distributed over the surface of the solid. C bar is mean concentration at the cross-sectional area. Finally, C sub I denotes the location concentration at the catalyst mesh I. Now, let's talk about the porous medium model. In porous medium model, we assume the reason with characteristic values such as the transmittance and inertial resistance factors of the real porous medium of the catalyst using porous medium. So in porous medium's equation can be explained by there. So delta P can be expressed like these terms. Also, flow in porous medium such as DPF, DOC, SCR are assumed as lambda rho. The last, I talk about the boundary conditions in this study. Among the turbulent models based on Navier-Stokes equations, a partial differential equations describe the internal flow of the after-treatment system. Is called RNGK epsilon model, which shows simple computation and good convergence characteristics was used in this study. In these conditions, urea injection pressures set as 3 bar. Also, urea injector was placed in the center of the reactor. Also, exhaust flow rate is in accordance with ISO 8178, which explains the emergency generators' best driving conditions. At table 1 shows boundary conditions of this PM NOx reduction system. Now, I talk about my study's analysis results. First, I studied the difference according to the presence or absence of mixer and mixer's shape. Filter types such as DOC DPF and SCR are grouped into one set of for scaled-down circular walls to minimize drop in flow rates in the filter. Also, I will check the internal flow velocity of the system. First, in DOC and DPF, the flow velocity marked 28 milliseconds, and in the relatively narrow reactor section, the speed marked 40 milliseconds, and the speed decreased to 25 milliseconds in SCR as the flow is extended again by the magnification tube. Figure 2 shows the velocity magnetic symmetry of standard PL mass reduction system. In this speed study, we found that influence of the gravity cannot be ignored when the flow speed is too low. So we need to find optimal design conditions for mixture that allow area to mix uniformity with emissions is important. Now let's talk about the urea mixer design. Blade angle was analyzed by varying in two ways, such as 30 degrees and 45 degrees, based on placing at the front end of the urea injector. So figure 3 shows standard mixer design, and figure 4 shows turbulence formation by mixer. In blade angle is 30 degrees, flow uniformity at the front of the SCR decreased. Overall gap pressures also increased from 48.8 millibar to 55 millibar. Why? Because mixer primarily formed turbulent flow in the exhaust gas flow, leading to uniform mixing. So mixer caused more uniformity by this study. Also, increasing the blade angle of mixer shows that urea is relatively concentrated in the SCR core, and the uniformity of flow drops slightly in the 1% range. Ammonia concentration biasing has the effect of suppressing the SCR reaction. It has a relatively low NOx reduction performance in this area. However, in the case of back pressure, increasing the blade angle to 45 degrees reduced by about 7%. Table 2 shows the ammonia distributions for with mixer blade angle. So, we knew that mixer improves the flow uniformity, but cause also increase of back pressure. The rise in exhaust back pressure in SCR catalyst should be as low as possible because it causes degradation of power output and emergency efficiency. Figure 5 shows a correlation between uniformity, back pressure, and mixer blade angle. And we knew that if we increase the mixer blade angle, uniformity also increases. Considering the correlation between back pressure and flow uniformity, it is most reasonable to design the blade angle is 45 degrees. Next, we studied ammonia distributions with mixer location. Table 3 summarized the distribution of ammonia according to the mixer locations. Case 2 had a relatively even distribution of ammonia compared to case 1, which was placed at the front of the injector. But in case 3, when two mixers were placed before and after the injector, strong turbulent flow was observed. In this situation, urea swirled and flowed, but the part that was not properly mixed was largely concentrated on the left side of the SCR cross-section. So we found out that case 2, in which the mixer was placed behind the urea injector, had even ammonia distribution and the highest flow uniformity of 96.1%. Case 3, the average flow uniformity was lower than that in case 2, and also back pressures rise more than 16 millibar. In conclusion, placing the mixer behind the urea injector is a design method that can simultaneously optimize the flow uniformity and also back pressure. Now, let's talk about the difference by SCR division angle. We conducted an analysis of a total of 4 division angle models. In the base model with 30 degree, a localized concentration occurred as part of ammonia moved away from the center of the cross-section. However, as the angle increased, the horizontal length of the division becomes relatively shorter. Then, length of the reactor can be obtained with the fixed total system length. This situation can improve mixing rate of exhaust gas and urea. Table 4 shows the ammonia distribution with SCR division angle. In figure 7, it shows the graph of the uniformity according to the division angle change. As the division angle increased, uniformity increased by the relative reactor length. However, above 60 degrees, significantly reduced flow rate and also pressure drops. And due to the influence of gravity, some of ammonia was forced at the bottom. So in conclusion, division angle must be designed not to exceed 50 degrees to obtain the best uniformity between the mixing length, velocity, and also pressure drop. Now, I talk about the conclusions of this study. In this study, a design was performed for a PM NOx after treatment device for emergency generator, and a safety analysis was performed to understand the change in flow characteristics according to mixer design and arrangement of SCR division angle in order to optimize reduction performance. Summarizing is as follows. First, when a mixer is stored, tolerance forms and the uniformity of the flow increase, but back pressure also increase. Second, if the mixer blade angle increase based on the base mixer, the flow uniformity decreases slightly. However, it is very efficient because the pressure formed by mixer is reduced. Third, if the mixer is placed in the rear of the urea injector, it can mix the flow more uniformly, and the uniformity of flow increase compared to when placed in front of the injector. If 2 or more mixers are placed, it creates large resistance to flow, so that the pressure increases significantly. Finally, in the fixed system in length, increasing SCR division angle more than 30 degrees increase the relative reactor length. This situation can increase the flow uniformity, but increasing by more than 60 degrees significantly reduce the flow rate, and some part of the ammonia concentrate at the bottom of the SCR cross-section. This is the end of my study. Thank you, everyone.